Today you have the biggest and greatest tomato plants in the country. Thank you, Neusrel, for these findings, and you lived happily ever after.
So this is a kind of introductory commercial here. You can buy software right here. No. So basically, the takeaway of this movie is the following. The methods we are applying in management science, structural equation modeling methods, are very good hammers, yeah, kind of hammers. And you might know this metaphor. If you have a good hammer, every product looks like a nail, right? But actually, in management terms, and most probably also in psychologics and so on, you don't really know if it's a nail or maybe a screw, right? So there's much uncertainty involved, which we cannot impose up front. So rather, we would need a method which basically is more flexible to nails and to screws, without knowing whether or not it's a nail or a screw. To be more specific, what are the limits of the structural equation modeling methods we know today? It's first of all, they nearly all assume linearity. And there are, of course, some clever attempts to overcome non-linearity assumption, like introducing a product term. But this is again kind of a conformatory approach. You have to know the kind of nonlinearity. Product term is kind of this kind of a form, and also you have to know which of your variables have that nonlinearity, because if you don't know it, you inflate your numbers of variables quite a lot. So what we need is a method that explores nonlinearities without knowing beforehand where the nonlinearities take place. We need that in management science to learn how the reality works. Why do we need it? Because we don't know. That's a given. And the same, and even worse it is with independency. So every model assumes, because it's a linear combination, the plus is always meaning independency of the drivers. They are added up. So that's an assumption. You saw with a plant, it is not met very often in reality. Yeah? Sometimes two factors needs to be the case in order to witness an effect. Again, there are attempts to overcome that, to build a product term. But again, you would need to know which variables interact with each other. If you have 20 variables, you have 400. You can do 400 product terms, which inflate your variables to an extent which is not feasible anymore. And product term is only one kind of interaction. Logically speaking, it's AND interaction. But there are an OR interaction or exclusive OR. There are many kinds of interactions. So this means we need to explore interactions which are not proposed up front. Why do we need it? Because it is the reality that our variables interact with each other. In order to model better the reality, we need methods that explore the interactions. Other things are limits. For instance, the methods are built that, for instance, only metric variables are used or only nominal variables are used. But in reality, variables have different scales. There are metrics, nominal scale, and so on. We need a method which is flexible enough to work with all kinds of scales. That is very important because only a holistic model, which includes all kinds of causes, can give true results, unbiased results. So we need a method that can handle the mix of scales. And lastly, the methods we have today have limited exploration capabilities. This means typically in management science or the social science, there are many different variables which might have an effect. And often it's too much, and we don't have hypotheses, strong hypothesis, research hypothesis, how they relate to the target variable. But there are some guesses that they might be. So what we would like to wish is to include more possible variables which have an effect in order to explore which ones are truly valid. Yeah. So, and this you can do only if you really have kind of a regulation techniques. Regulation means you not just model by assuming everything is kind of have an impact, but you try to minimize the complexity of the model itself. So there is an inherent learning method that tries to eliminate variables. That's a regulation technique. So basically, that are the requirements we need in practice. We need to make to learn better from data. And the universal structure modeling is building on universal functional approximator, which, for instance, to this class belongs neural networks. And there are other, for instance, support vector machines and so on, that are methods which are can be used to achieve that. They are explorative, they are very flexible, they can model unknown nonlinearities, handle differently scaled variables, and are able to or include regulation techniques. Let me go show you more in detail how the universal structure modeling is built up. So basically, you have two levels. The first one is measurement model, where you have the option to compute out of manifest variables a latent variable, and then once you have the latent variable, you can, using regression techniques, build the structure model. So from this stage, it's kind of a partially square path modeling. Most of you might be familiar with structure equation modeling, covariance-based structure equation modeling, which works a little bit different. Yeah, covariance-based structure equation modeling works by optimizing the kind of takes the correlations and out of this optimizes and finds path parameters that reproduce this covariance matrix. Another method which does the same job but on a different approach is partially squares partial path modeling. And it works like described. There is build the measurement model first, then compute the structure model using regression, and go back and forth. So then, with the updated latents, you then again update the measurement model. From this point of view, it's kind of partially squares path model, which has pros and cons. And the pro against covariance-based structural equation modeling is it works with much less sample size, and it's more flexible or not so vulnerable against misspecification. we use this the structure of partially squares, partial buildings, but extend the capabilities by using neural networks. Neural networks are nothing else than multivariate regression methods, but more flexible, which are able to encounter nonlinearities and interactions. So basically, in the structure model, these are regression models. So we use their neural network. And the same is true for the measurement model, and it depends whether it's a formative or reflective model. Yeah? If it's a formative model, in the first step, it's initialized applying a nonlinear principal component analysis, and in the interaction, then standard neural network is used. So, but in principle, you can stick with a linear measurement model here, and you can only decide to use neural networks in the structural model. So, if you use neural networks, you have one shortcoming, because actually the researcher is interested in learning how the latent 1 impacts latent 3, but the neural network is the black box. I don't know what the separated impact is. So we need the second step, or the third step basically, the post-processing. Only this post-processing enables me to understand the separated effect of latent 1 on 3, and to uncover the nonlinearity which take place. The same is with interactions. Only this post-processing stage can uncover two-way interactions, can also uncover three-way interactions, but then it's more difficult to visualize that.